How do you put a telescope in orbit that's bigger than the rocket that's going to launch it? Is that even possible? It's easy to imagine that everything that exists in space, or at least in our solar system, is already there. As far as we know, everything in space is quite old, so the idea of something brand new appearing there seems highly unlikely. However, the opposite is true. The James Webb Space Telescope, by taking incredibly precise photographs of the cosmos, has caused quite a sensation worldwide. The beauty of science is that it welcomes new information rather than rejecting it. Despite the warm reception to new information, some of what the telescope is seeing is still puzzling and perplexing. What have scientists observed from the James Webb Space Telescope that has them baffled? What mysteries about the beginning of time as we know it has the telescope unlocked so far? Let's find out. Recently, NASA, the European Space Agency, and the Canadian Space Agency teamed up to give astronomers around the world an extraordinary gift: a chance to glimpse into the past at the creation of the universe and the edge of time itself. The James Webb Telescope, hailed as the premier observatory of the next decade, stands as one of the greatest scientific achievements of our time. It opened this otherworldly window into creation not as a philosophical theory, mystical time machine, or artistic metaphor, but as a tangible instrument. On December 25, 2021, this massive infrared telescope, more commonly known as Webb, was launched into orbit with the goal of capturing images of the unknown and unraveling the mysteries of our hidden cosmos. The cutting-edge infrared detection equipment outfitted on Webb enhances the unique perspective of the universe that Hubble has provided humanity. From its vantage point in low Earth orbit, Hubble has captured numerous never-seen images of remote regions and historic periods of our universe. Exploring the history and evolution of galaxies, stars, and nebulae, it has described the characteristics of black holes, exoplanets, and the accelerated expansion of our universe. This groundbreaking work earned the Nobel Physics Prize in 2011. Webb represents the next phase in our collective adventure of discovering the universe's secrets and searching for life beyond Earth. Hubble's images have defined modern astronomy, opening our eyes to what lies beyond and sparking our existential curiosity. As NASA puts it, we need to see farther and deeper. Webb can peer back to the beginning of time, while Hubble can only go as far as 500 million years after the Big Bang. How is this possible? The most recent space telescope boasts several advantages over early emissions. Its size is the first notable feature. JWST has a 6.5 m mirror made up of 18 gold-plated hexagonal parts. This behemoth can capture light from objects 6 times faster than the 2.4 m Hubble Space Telescope because it can gather more light. However, the true game-changer is JWST's sensitivity to infrared light. The Space Telescope can detect wavelengths between 0.6 to 28.5 micrometers, spanning the mid-infrared to the red end of the visible spectrum. While the majority of Hubble's sensitivity focuses on visible light, its optics are tailored to capture radiation from 0.09 micrometers in the ultraviolet to 2.5 micrometers in the near-infrared. Astronomers can observe galaxies that formed fewer than a billion years after the Big Bang by utilizing the infrared spectrum. These distant objects emit visible and ultraviolet light, but due to the expansion of the universe, this radiation is now emitted at longer infrared wavelengths. The only way to observe these young galaxies close to Earth is through infrared observation. This also applies to newly formed stars. Infant suns are surrounded by dust which scatters visible light, obscuring our view but allowing infrared energy to pass through. Infrared radiation is invisible to humans. The hues of images captured by JWST differ from what the human eye would perceive. To simulate how the eye sees, scientists often map longer infrared wavelengths to the red end of the visible spectrum and shorter wavelengths towards the blue. However, occasionally this pattern is changed to highlight specific details more effectively. JWST serves as an all-purpose observatory. Despite its focus on distant galaxies and star formation, its strong infrared capabilities enable it to discern features in solar system objects that regular telescopes cannot observe. Studying cloud belts on gas and ice giant planets, monitoring cloud formations on Titan, investigating Pluto's atmosphere, and probing many smaller asteroids and trans-Neptunian objects throughout the outer solar system are just a few of its early achievements. When NASA's Double Asteroid Redirection Test collided with the asteroid Dimorphos, JWST even captured a glimpse of the event. This allowed NASA to study the object's ability to alter the course of potentially hazardous asteroids that might cross Earth's path. Despite the efforts of planetary scientists to uncover the myriad secrets of our solar system, over 5,000 known exoplanets in our galaxy remain unknown. Most of this additional information lies beyond the capabilities of Earth-based telescopes, including Hubble. However, JWST has already begun to change this situation. While not specifically designed for exoplanet discovery, JWST identified one around the red dwarf star LHS 4175, 41 light-years away from Earth. This planet's diameter is only 1% smaller than Earth's, but it orbits its sun in just 2 days and boasts a temperature a few hundred degrees warmer than Earth. JWST's greatest strength lies in its ability to study exoplanet atmospheres. By observing transits with its potent spectrographs, astronomers can investigate the chemical composition of these worlds. The majority of compounds of interest to exoplanet researchers are found in the infrared region of the spectrum. JWST's exceptional resolution has allowed for the discovery of various compounds on exoplanets, including water, sulfur dioxide, carbon monoxide, sodium, potassium, and carbon dioxide. The gas and dust stellar incubators known as nebulas are where planets and their host stars develop. However, despite their beauty, these clouds conceal the essential processes occurring within them from the outside world's view. JWST's infrared vision has begun to reveal these hidden habitats. For example, the Eagle Nebula, famous for its Pillars of Creation photograph taken by Hubble in 1995, was one of JWST's initial targets. While Hubble mostly observed opaque dust and cold gas, JWST discovered several stars that had already emerged from their natal cocoons. These young stars, visible outside the shadowy pillars, are identifiable by their diffraction spikes in images captured by reflecting telescopes like JWST. These discoveries offer valuable insights into the formation and evolution of celestial bodies, shedding light on the mysteries of our universe. In their course, stars develop into mature stars, but JWST has discovered even more recently formed objects called protostars. These protostars are still in the process of absorbing gas and dust from their surroundings. Occasionally, they emit material jets that strike their dense environment, causing them to radiate intense red glows. The 2 lower pillars are among the best examples of this phenomenon. These protostars are estimated to be only a few hundred years old, according to astronomers. Star formation occurs throughout the universe, and JWST scientists are eager to investigate its various manifestations beyond our galaxy. Within our local group, 2 important locations are the Large and Small Magellanic Clouds, the 2 most massive satellite galaxies of the Milky Way. Understanding these galaxies is crucial because they contain about half the quantity of metals produced by massive stars as the Milky Way. This situation resembles conditions that prevailed when the universe was only 2 or 3 billion years old and galaxies were producing stars at a maximum rate. The galaxies formed during this cosmic noon, including those we see now, were shaped by the explosions during this period. The Tarantula Nebula, located in the Large Magellanic Cloud, is the closest object in the Magellanic Clouds to reflecting these chaotic times. The Tarantula Nebula, the greatest star-forming zone in the immediate universe, creates stars at a furious rate. Approximately 820,000 stars have been catalogued by astronomers to date, and the enormous reserves of hydrogen and helium the nebula holds should be sufficient for hundreds of thousands more. The bright star cluster R136, near the core of the nebula, contains numerous stars weighing at least 100 solar masses. JWST's initial observations have revealed incomparable detail of the Tarantula Nebula. In the middle part of the nebula, a sizable bubble has been cleared out by the intense radiation and stellar winds of the big stars. In R136, only the densest neighboring locations, which likely contain baby stars of their own, can withstand this assault. The Tarantula Nebula provides astronomers with a close-up perspective of the conditions they would encounter as they further investigate the cosmic midday. Observations of nearby phenomena often help scientists understand more distant ones more clearly. Just as star formation in the Magellanic Clouds sheds light on similar processes in the far reaches of the universe, planets in our solar system contribute to the study of exoplanets. Similarly, Research on interacting galaxies directly contributes to our understanding of the tumultuous beginnings of the cosmos. JWST was built to study ancient galaxies formed at the beginning of the cosmos directly, and scientists have been eagerly testing this capability. However, neighboring regions can frequently serve as analogs for older, more distant environments. A deep-field image of the galaxy cluster SMAC 723 in the southern constellation Vela was one of JWST's first pictures and the first one made available to the public. This exposure, which took 125 hours compared to weeks for Hubble's different deep fields, captures galaxies in incredible detail. These distant galaxies, even fainter and farther away than what Hubble could detect, are visible in the SMAC 723 cluster. The light we receive from this cluster is from approximately 4.6 billion years ago. However, due to the cluster's enormous mass acting as a gravitational lens, galaxies located further away, including those present within a billion years of the Big Bang, are also visible. The smallest galaxies in the field, situated furthest away, do not resemble the more developed spiral and elliptical galaxies closer to our planet. A significant discovery made using the massive galaxy cluster Abell 2744 in Sculptor as a gravitational lens is the observation of two galaxies barely 450 million and 350 million years after the Big Bang, respectively. These galaxies appear unusually brilliant and likely began to form barely 100 million years after the Big Bang. Researchers are unsure if these galaxies consist of numerous dim stars or a few exceptionally bright population 3 stars, believed to be the first stars in the universe, composed solely of hydrogen and helium. Another recent finding by the James Webb Telescope is the imaging of a group of galaxies only 600 million years old from the start of the universe. While the age itself might not be particularly fascinating, the circumstances surrounding this discovery are revolutionary. By pointing telescopes towards the cosmos's origins, we can witness events that occurred billions of years ago when their light eventually reaches us. These enormous galaxies, only 600 million years or less from the universe's beginning, pose a challenge to our current understanding of galaxy formation. Their rapid growth raises questions about the processes involved and challenges long-held scientific theories. These discoveries highlight the primary motivation behind launching the James Webb Telescope, to push the boundaries of our knowledge and challenge accepted scientific truths. What more Webb will discover remains unknown, but it is certain to continue reshaping our understanding of the universe through its precise observations and deep imaging capabilities. The James Webb Telescope is poised to unveil more mysteries of the cosmos and potentially revolutionize our comprehension of the universe's early epochs and galaxy formation processes.